I am Anil Kumar. Welcome to my series on calculus. We are also doing a fast track calculus where we are going to complete the course in just 2 weeks. Now, this is our unit number 6, in which we'll be learning how to sketch curves for different kinds of functions. So, when you are sketching any particular curve, we do have an algorithm to follow. So, we'll discuss what is the algorithm for curve sketching. Now, this algorithm is basically dependent on the type of function. Most of the time, it has a set format. We need to go through all the important things to get a good graph. However, there are very special features for different types of functions. So we'll see what is more relevant when we sketch a polynomial, or when we sketch a rational function, or when we sketch a radical function. We'll actually complete this with exam practice test question, which will be kind of your assignment. You can always write back to me. I can give you additional practice questions and set of videos to look into so that you can practice and be perfect in this particular topic. So let's begin with how to sketch polynomial graph. So I've taken an example here, which is example 1. We'll sketch the graph of the function, which is x plus 1 times x minus 2 whole square. Now, those of you who have done functions, they can actually sketch this particular graph. However, without calculus, two things are difficult to find, and those are the local maximum and minimum points, right? The extrema, and also it's very difficult to find the point of inflection. Now remember, what is point of inflection? So let me write down. Point of inflection is where the concavity changes. Correct. So that is a very important point to sketch accurate graph. In general, we are going to follow this particular algorithm. So here is the algorithm for curve sketching. We are going to deviate from this algorithm depending on the type of function, right? So definitely you should know what is the domain and range of the function. It is very easy to find the y-intercept, so never miss that part. X-intercept, I will treat this as optional in some cases, right? But for polynomials, it is a very critical part. Then find zeros and the end behavior. Now remember, when you find zeros, you have to also look into the order of zeros. That is to say, sometimes we say multiplicity, right? Now the question for you is, what is the difference between, let me write down the question. What is the difference between x-intercept and 0? Well, at x-intercept and at 0, the y value is 0. But the idea is, what is the difference between these two things, right? So x-intercept and 0, zeros are different things actually, right? So how are they different? So that is why purposely in this particular algorithm, I'm mentioning two things, and that is find the x-intercept and also find zeros with their order and multiplicity. Well, at any particular point of a zero, if we know the zero, then we know the behavior of the curve at the x-intercept, right? So let me write down here, zeros provide behavior of curve at x-intercept. Correct? So now I think that will be a good hint to answer this particular question. Correct? So zeros have additional information. They tell you that how does the curve behaves at the x-intercept, and that they know only because of the number of zeros at that point, which we call order or multiplicity, right? Okay. And then once we know the characteristics, so these things here define the characteristics basically, right? So these are characteristics. Now after that, what we do is we try to find out the first derivative. And once you find the first derivative, we analyze the first derivative to find extrema. So we get from extrema local maximum and local minimum. Well, first derivative also tells you about increasing and decreasing behavior. Then we'll find the second derivative, and once you find the second derivative, we will know what is the concavity and what is point of inflection. Perfect. So let's take examples to understand details. So in the very first example, I've taken up a polynomial. The function is x plus 1 times x minus 2 whole square. Well, one option is to expand and simplify, but not necessary, right? So what we've done here is expand and simplify. But it is not necessary. It helps, although, right? Since the derivatives become simpler. If you don't do that, you may have to apply the product rule for derivatives. That's it. Okay. Now, but the factor form gives you additional information, and that too about zeros, right? Okay. So first step what we did was actually we have it in different forms. We actually expanded and simplified this as x cubed minus 3x squared plus 4. Now once you get that simplified form, first derivative and second derivative becomes simpler. So first derivative is 3 times x squared minus 6x. When you factor, you get 3x times x minus 2. And the second derivative, from here, better to do 3x squared minus 6x derivative, which is 6x minus 6. So you get first and second derivatives. Now, we'll analyze these later, but now let's look into the characteristics of a polynomial. As far as the polynomials are concerned, in general, we know domain is all real numbers. The degree of this polynomial is what? Well, the degree is 3, right? So we know here that the degree is 3. And we also know that leading coefficient is positive, right? Is positive. Now, well, degree 3 means odd degree. That means for sure range is all real numbers. Perfect. It goes from quadrant 3 to quadrant 1, right? So it goes from quadrant 3 to quadrant 1, right? So that is how the general behavior will be. Positive leading coefficient means it will end up in quadrant 1 and opposite ends is degree 3. Okay. Now, very easy to find the x and y intercepts in this particular case. So we should take this opportunity to substitute the value 0 for x to find the y-intercept. So when you substitute 0, you get the y-intercept as the constant 4. The x-intercept is very clear from the factored form. So we know x-intercept is at minus 1 and 2. Easily, you could read from the factored form given to us. Now from here, we know this particular 0 is linear at 1, and at 2, it is of order 2, like a quadratic function. It will turn at that particular point, right? So we are saying that as far as the zeros are concerned, then order is 1 at x equals to minus 1, but the order is 2 at x equals to 2, right? So order makes a difference, right? So order really means something like this. We found that the zeros are at minus 1 and at 2. And we also know that the end behavior is going from this side to that side, correct? Now, since we have x-intercept at -1 of order 1, that means the graph will simply cross this, and at 2 it is going to turn. So basically, from this particular characteristic itself, we do get something like this, right? So we have a function which is, that is our solution. And we have already found that the y-intercept is known to us. This is also known, and that is also known. Now, what is not known to us is the point of inflection where the concavity changes, the, the maximum point, and that is the minimum point, which is kind of clear. So we don't have the maximum point and the point of inflection. So these are the two things which are actually missing, and for which we are going to use the first derivative and the second derivative. Does make sense to you, right? So therefore, let me just again emphasize on what do we need to figure out. And that's why I was saying that when you're trying to graph a polynomial, the two things missing, which we come to know from calculus, is local maximum minimum and the point of inflection. Is that clear? Okay, so now let's continue and see how to find this local maximum and minimum. So definitely we'll begin with the first derivative. Since the function was written in the simplified form as x cubed minus 3x squared plus 4, the derivative will be 3x squared minus 6x, which if you factor, you get your critical numbers. Now, here, whenever we talk about the polynomials, instead of saying critical numbers, we say stationary points, right? So let me mention critical numbers also here. So we could say either critical numbers or stationary points. Now there is one difference between the two. So that is another question for you, and that is, what is the difference between stationary point and critical point, let me say, okay? So you need to figure out the difference between these two things also. Okay, so we have now the first derivative, which is 3x times x minus 2. So clearly the critical number or the stationary points are at x equals to 0 and at x equals to 2, right? So we have two stationary points. We need to analyze which one of this could be a local maximum or could be a local minimum. So for that, the criteria is that the function should be changing from increasing to decreasing or from decreasing to increasing. So we analyze the first derivative. So for that, we take a test point on either side. So these two zeros divide our plane into three regions, right? So we have three regions here. One region here is from minus infinity to 0, right? The other one is from 0 to 2, and the third one is from 2 to infinity. So within these intervals, we'll take a test point. So minus 1, 1, and 3 are respectively the three test points. The factors which provide us the information about the first derivative are 3x and x minus 2. So at these test points, we are provided their sign, right? So for 3x, it is negative for minus 1, positive and positive for 1 and 3. X minus 2, if I substitute minus 1, I get negative. For 1 also it is negative, but for 3 is going to be positive. The function is product of these two. Two negatives will give you a positive, right? And a positive and a negative will give you a negative. And two positives definitely will give you positive. Now, positive means what? It means increasing, right? So this means increasing. And negative means decreasing. So as shown by the arrows, the graph is increasing and then decreasing. So we definitely get a maximum at x equals to 0. Perfect. So at x equals to 0, the point is 4, y value. Substitute 0, you get this 4. So we know that in this case, the maximum occurs at 0, 4. Now the minimum will occur at 2 since the function is decreasing in the interval from 0 to 2, and then from 2 to infinity it is increasing, and therefore we get a minimum at 2, x equals to 2. So when you substitute 2 here, this factor becomes 0, and as expected you get 0 for y value. But anyway, we found very important points, and these are the maximum and the minimum points on the polynomial graph. Now, we'll find the second derivative from the very first derivative which we found. So the function is x cubed minus 3x squared plus 4. The first derivative was 3x squared minus 6x. So what is the second derivative? Well, 6x minus 6. So that becomes the second derivative for us, which in factored form can be written as 6 times x minus 1. So that gives you one critical number, correct? So here we have one critical number. So let's say critical number at x equals to 1. So we need to analyze on either side of x equals to 1. So in this case, we again will go with our interval table just as we worked out earlier. Test point here is 0 on the left side, 2 on the right side. So when I substitute 0 here, I get a negative value. Perfect. But when I substitute 2, I get a positive value. Negative means concave down, positive means concave up. So clearly, concavity changes, and therefore we have a point of inflection at x equals to 1, right? Since concavity changes. Right? Which leads to point of inflection at x equals to 1. So we'll substitute 1 in our expression, and then you can calculate the value, which is 2. And that means that we have a point of inflection at 1, 2. So now we have all the information to graph the polynomial. So it is a good practice to summarize all the information and then sketch the curve. So let's recall. So we got y-intercept of 0, 4, the x-intercepts at minus 1 and 2, the zeros order. This order was 1 and then the order was 2 for 2, right? End behavior. Since this is a degree 3 polynomial, right? So the end behavior is degree 3, which is odd degree, positive leading coefficient. So that gives you the end behavior that goes from this side to that side, correct? Which is written as when x approaches negative infinity, y approaches negative infinity. So you are in quadrant 3. When x approaches positive infinity, y approaches positive infinity. You land up in quadrant 1. So you are in quadrant 1 landing, and you begin from quadrant 3. Whenever you look at a graph, it is very important to see the graph from left to right always, right? Now we know our points. We got the local maximum and minimum point. Those are marked here. The point of inflection, which we found from change of concavity. And there you go. Here we have a graph. You can clearly see that this is a 0, which is linear 0. And that is a quadratic 0, right? So that is basically a 0 with order 2. Correct? And this one is 0 with order 1, linear 0. That is what we meant by zeros and their multiplicity. Perfect. So in polynomials, zeros are very important. That is to say, you have to find out the x-intercept and the number of zeros at that particular point. Perfect. Now let's take the next example, which is of a rational function, right? So here we have the next example, which is rational function, example 2. Sketch the graph of x squared minus 3x plus 6. Do not determine the second derivative, right? So sometimes it may not be very critical. We have mentioned clearly here. Now, when you have a rational function, what is critical? So whenever you have a function, there's something critical about it which you should know and you should definitely find answers for. So whenever we have a rational function, the critical point is it is important to find the asymptotes and behavior near asymptotes. Perfect. So in polynomials, it was the zeros and their multiplicity which was very important. It was the local minimum and maximum along with the point of inflection. But when we're talking about a rational function, it is the asymptotes which are most important, and we have to focus on behavior near the asymptotes. Perfect? Okay. But, well, picking up things from our algorithm, definitely we'll add more to that. But the most important is the vertical asymptote, horizontal asymptote, or oblique, right? So one of them will be there, maybe there, right? So both will not be there. So maybe, right? Okay. Domain and range, y-intercept, x-intercept, find the derivative to analyze for extrema. So that is kind of important since we know in this particular graph, we're going to have some local maximum and minimum. So always local maximum minimum is kind of critical. Now as the question suggests, see what we have here is something like this. We have x squared minus 3x plus 6 over x minus 1. Now that means degree is 1 higher, right? So the numerator degree is higher. One plus denominator degree. That means what? That means in this particular case, we have an oblique asymptote. Is that clear to you, right? So how will you find oblique asymptote? You will have to divide the numerator by the denominator. So some of you could do long division, which is x squared minus 3x plus 6. Divide this by x minus 1. And what you get in the quotient will be your equation for the oblique asymptote. Perfect. So that is kind of important to understand. And the second thing is that the denominator gives us the vertical asymptote. We cannot have denominator as 0. So x equals to 1 is your vertical asymptote. Perfect. Now let's see how to find these parameters. So let's begin with the vertical asymptote itself. Equating denominator to 0, we know at x equals to 1, we have vertical asymptote. Now in this case, since the degree is higher, we do not have a horizontal asymptote, but we do have oblique asymptote. Now, how do we find oblique asymptote? For oblique asymptote, I have done synthetic division here. Some of you may be familiar with. If not, watch some of my videos. Otherwise, you can actually do the long division as I was suggesting earlier, right? So basically, we write the coefficients which are 1, minus 3, and 6. So 1, minus 3, and 6 are these coefficients. X minus 1 is the divisor, so 1 comes from this x minus 1. What makes that 0? And then we bring down the term which is 1, and then we multiply this, we times it and write it there, right? And then we bring down the sum of these two. So you add them up. So when you add minus 3 and 1, you get minus 2. Then you multiply with 1 and then put it there. And then when you add it up again, you get this as your remainder. Correct? However, what we get earlier is the quotient. These are the coefficients for the quotient. So x minus 2. So x minus 2 becomes the quotient. Remainder of 4, we'll still need to divide by x minus 1, and therefore we can now write the function f of x as this. Is that clear to you? So whenever you're working with a rational function, if the degree of numerator is higher, you like to simplify it, right? Write it in the simplest form. So divide it. And then just as you do in fractions, correct? Okay, but that gives you a very important result, which is the oblique asymptote of a line is a line which is y equals to x minus 2. Now it is important to understand how do we approach this particular asymptote. What I'm trying to say here is we figure out that the asymptote is kind of a line which is, let me sketch on the side just to explain a bit, right? So x minus 2 will be a line which has a positive slope of 1 and goes through minus 2. So what we're trying to figure out now is how does the curve of this rational function behaves when x is approaching negative infinity. So if you put a very large negative value for x, in that case what happens? Well, this particular part, which is plus 4 over x minus 1, becomes negative. And therefore, what happens is that it approaches from above, right? So because this is something, some negative thing, very high negative, minus some value. Is that clear to you? So you'll be approaching from above. Okay. Now, I mean, there's something error here. We have written both negative here. So let's begin with positive first. So if I write x as positive, let me make one of them positive. Let me make this positive. Okay. So, okay. So if I make this as positive, this is a higher value. So in that case, we are approaching from above. Well, so I should do the next one positive. So I should do this one positive, right? Okay. So if x is positive, then we are approaching from above. That is what I'm trying to say. Is that clear to you? Approaching from above. Because we are adding something to the line, right? So line plus something, small value. So we are approaching from above, correct? That's what it means. Now, we have a vertical asymptote at x equals to 1. So definitely there is an asymptote here. So we expect this graph to be kind of like this. So we'll find the second derivative to find this particular turning point. Is that clear to you, right? We also figure out that there is a y-intercept, since if I substitute x equals to 0, we get 6 on the top. So 6 is your y-intercept. So the graph is actually crossing at x equals to minus 6. When x equals to 0, 6 over 6 is minus 6. Sorry, minus 6. So when I write x equals to 0, what do I get? I get 0 minus 0 plus 6 over 0 minus 1. So this should be minus 6. So we are crossing the graph somewhere here, right? So the other interesting thing is when x is large negative value, in that case, the line is approaching from below, means it is kind of like this. Does make sense to you, right? So now everything comes together. And from this particular situation, you can see we do have turning points at these 2 points, which we need to figure out from first derivative. So therefore, the question also specifies that you need not do the second derivative. You can fairly, accurately sketch this particular graph using just the first derivative. Is that clear to you? So let me draw this attention. Do not determine the second derivative. That's very critical, right? Reason being that when you find the first derivative, it is kind of complicated, right? So you can save some time but still get the same result. Okay. So we have made some correction here. So it should have been, I just did not make it positive. So when x approaches negative infinity, in that case, the curve approaches the oblique asymptote from below, like shown here. That's what we mean by below. And this is the line which we have shown here. This is your line L, oblique asymptote, right? Let me write oblique asymptote. So we are approaching this line. That's why it's called oblique asymptote. When you're approaching x towards positive infinity, we approach this line from above. The y-intercept confirms the behavior of the curve. Correct? So what we have done here is we have analyzed close to oblique asymptote, and then analyze close to the vertical asymptote. Now, vertical asymptote is at x equals to 1. You have to see what happens when you approach this vertical asymptote from left side and the right hand side. So we say when x approaches 1 from the left side, so that becomes from the left hand side, correct? In that case, it approaches minus infinity. Now, sometimes you could use the calculator. So just calculate a value which is slightly less than 1 in this case, which is 0.9. So substitute zero point 0.9 in the function itself, and you'll find that you get negative large value. So you're approaching negative infinity. Is that clear to you? Right, this negative infinity. The asymptote, vertical asymptote. Now, when you are approaching from the right side, you find that this value is very large positive. And therefore, we can write that when x is being approaching from 1 from the right side, y approaches positive infinity. So we clearly know behavior near the asymptote. Now, let's find the derivatives. We can apply the quotient rule to find the derivatives, right? So here is the function given to us. We apply the quotient rule, denominator square, derivative of numerator, x square minus 3x plus 6, derivative is 2x minus 3, times the denominator minus, derivative of denominator is 1. So I didn't write 1. You could always write 1 here. Does make sense. And then the first part. And when you simplify it, what you get is kind of like this, right? So you can actually simplify and get simplified form. It is good to write in factored form to find the critical number. Now, we had a question saying, what is the difference between critical number and stationary point? Now, remember here, critical number means that the derivative could be, when I say critical number, in that case, we are looking when the derivative is either equals to 0 or does not exist. Perfect. So, critical number is a general term. For polynomials, we use stationary points since they are smooth curves and the derivative always exists, right? So, does not exist is not there. So you could use stationary there. But in this particular case, we see that at x equals to 1, we do have a critical point, and that point divides our plane into two more regions, correct? So we have three critical numbers to work with. One is x equals to minus 1, the other is x equals to 3 from the numerator, where we have zeros, right? So these are the zeros. However, at 1 we have a vertical asymptote. Now this value can never be included in your solution, correct? It is not in the domain. Now we take a test point just as we did earlier, and we'll analyze this interval table to find what is happening to increasing and decreasing behavior of the curve. Test points are at minus 2, 0, 2, and 4 within the intervals being divided by these critical numbers. Now these are each factors, right? So we have all these factors, the 2 in the numerator and the 1 in the denominator. The square term is always positive. We don't have to think much about it. But for the other two, substitute the test points and write down the signs. We are not interested in values. We are only interested in positive and negative sign. Clear? Now remember, even number of negatives will give you positive, odd number of negatives will give you negative. And therefore, we do get a result here that the derivative is positive in the interval from minus infinity to minus 1. It is negative between the interval minus 1 to 1. Then again negative in the interval 1 to 3, but positive thereafter. Positive means increasing, negative means decreasing. And here you see we have a maximum, correct? Since the graph is increasing then decreasing, nothing here in between, right? But a minimum at 3. So we have a maximum, local maximum, and a local minimum
as shown here. Substitute the value -1 to get the value of 3, right? And substitute the value of 3, sorry, these are two values. At -1 you get -5, and at for 3 you get 3. So you get these two values, -1, -5, and 3, 3. These are your maximum and minimum values. Now, we'll summarize all the results. So here we have the summary of the results which we just did all the calculations. We know that the y-intercept is at -6. Okay, so this is not 6, 0 and -6, right? So y-intercept is at -6, clearly shown here. And we have a vertical asymptote which is right there at x equals to 1. We have a straight line which is oblique asymptote, and the equation for the oblique asymptote was calculated as y equals to x minus 2, right? So you see that y-intercept for the line at -2. The graph is approaching. So when you are approaching from negative infinity, you approach from below. Do you see that? From below. So that is when you are approaching from negative infinity. However, when you are approaching from positive infinity, you approach from above. And that's what we mean. Approaching the oblique asymptote from above. Clear? So that is, I think, now absolutely clear looking into this beautiful graph. Okay. Now, vertical asymptote, we analyze that when you're approaching from the negative one side, so you're going to negative infinity. If you're going towards the positive side, from the right hand side, you're approaching positive infinity. Then we have two critical points, which are local maximum and minimum, maximum at -1, -5, and minimum at 3, 3, correct? So those are the points, right? This is 3, 3. Perfect. So that is how you're going to get the graph of your rational function. So I hope you understand that when you're talking about rational functions, the critical thing to work is asymptotes and behavior near asymptotes. Clear? These two things are very critical to sketch a rational function. Now let's take another example which is based on surds. So we have radical functions here. I'd like you to pause the video, you know all the concepts, sketch the graph of this function which is x to the power of 5 over 2 minus 10 x to the power of 3 over 2. Once again, the method to or the algorithm to follow is kind of same. You need to find the intercepts, and the best thing is you need to find the first derivative, analyze the first derivative for local maximum minimum, find the second derivative which will give you the concavity and the point of inflection. So we'll focus more on analyzing the first and the second derivatives in this particular case, right? Now, another important thing here is that since we have a radical function, we need to look into its domain. Since it has a restricted domain, x is not equal to real numbers in this case. Perfect. So the function is x to the power of 5 over 2 minus 10 times x to the power of 3 over 2. Now in this case, square root type of things, we cannot have x negative. So x has to be greater than or equal to 0. That's kind of important. So whenever you work with radical functions, important thing is to work in restricted domains. Perfect. So x equals to 0 is a critical point here. However, we cannot approach this point from the left side. So keep that in mind. So I've made a note right in the very beginning of this particular section so that you pay attention to it. Origin is a critical number. We'll just find it out. Okay. Since it is an endpoint, we cannot check nature of the graph on its left side while analyzing the first and the second derivatives, right? But we can analyze on the right side. So let's begin by finding the y-intercept. So when I say f of 0, That means we are finding y-intercept, correct? And then we can find some critical values. What is the value of function at 1? At 1 it is minus 9. And then we have this particular function here. We find the x-intercepts. When you factor this, look at the factoring part. So we have simplified and factor this function. Now when you factor this, we get x equals to 0 or x equals to 10, right? So these are the 2 points which are your x-intercepts, x equals to 0 and x equals to 10. Now find the first derivative using the power rule. So you have the first derivative written here in the simplified form. So you get 5 over 2 x to the power of 3 over 2 minus 10 times 3 over 2 times x to the power of half, right? So 3 over 2 minus 1 is half, correct? 5 over 2 minus 1 is 3 over 2. You can take x to the power of half as common. You get x minus 6 in the factor, and therefore we have now two critical numbers which are at x equals to 0 and at x equals to 6. So we'll try to analyze the first derivative. Okay, so here is the analysis for the first derivative. So we know that there are two critical numbers, one at x equals to 0, the other one at x equals to 6. On either side, we should be taking points to check. However, since x equals to 0 is endpoint, we can only check on the right side. So we have only one point which is on the right side. But for x equals to 6, we have on both the sides. Now these factors, when you multiply, you get your function, and the function sign changes from negative to positive, and that gives you a minimum. Perfect. Same strategy which we applied earlier will be applied now. So at f equals to 6, x equals 6, we get a value. So calculate the value. You may have to use the calculator for this particular case, right? So calculate. So you can round your answer to, let's say, 3 significant figures. You get your value. That f of 6, we have a minimum, which is minus 58.8. Now, let's find the second derivative. We know that the first derivative is this, which we just figured out right there, correct? So first derivative, we can now differentiate this to find the second derivative, factor as we did earlier to find the critical numbers. Critical numbers again give you x equals to 0 and at x equals to 2. Analyze using the interval table for both these. So right side of 0 and right side of 2, right? So we get both sides of 2 in fact. So when you work with these, you find that the second derivative is negative on the left side of 2, but positive on right side of 2. That means the concavity changes, correct? So we have concavity changes. At x equals to 2. So at x equals to 2, we have a point of inflection. Is that clear to you? Correct? So that is how you could actually figure out point of inflection, local maximum and minimum points. So in this case, we have a local minimum and a point of inflection. So let's move now to sketch the graph. So now let's summarize all our learning. So we are going to sketch the graph of the function, which is x to the power of 5 over 2 minus 10 times x to the power of 3 over 2. Now in this case, we found that the domain is to the right side of origin, including the origin, and we also found the minimum point. Since we have a minimum point, which is being marked here, range is equal to and greater than this particular point. Then we have the x-intercepts at 0 and 10, so mark those x-intercepts at 0 and 10. Now, from the concavity, which we figured out, all this is from the second derivative, right? We have this is increasing and decreasing interval. So increasing and decreasing interval, local minimum, is from the first derivative. So we get this local minimum since it is decreasing and then increasing, correct? So we get the local minimum. The other part is about the concavity, which gave a point of inflection, and that is, you can see that in this part it is concave down, right? This portion is concave down. And this portion here is concave up. And so in between, we do have a point of inflection, which is at 2 minus 22.6, right? So substitute the value 2 in the function to get this particular value. And then you can sketch your graph by connecting a smooth curve as shown here. Is that clear to you? Perfect. So we have seen three examples, all of different kinds: a polynomial, a rational function, and a surds. Now, here are your test questions. So what we have done here is taken three questions. Uh, the very first one is a rational function, right? Rather, we have taken two rational functions in this case. Both are of different kinds. So the very first question here is, you need to use the algorithm for curve sketching to graph the following functions. So that is your particular function. Well, these are the links for solution. So links of my YouTube videos which can provide you the solution. Okay. So we have a rational function here, then again a rational function and a radical function. Now in the rational function, you find that the numerator degree is lesser than the denominator degree. So we have a horizontal asymptote in this particular case, right? Plus of course a vertical asymptote at origin. In this particular case, the degree of numerator is higher. So we have in this case oblique asymptote, and we do have a vertical asymptote. So they are slightly different, but you need to find the asymptotes, work on the asymptotes, and how the graph behaves near the asymptotes becomes a key in this particular case. Second, in both these cases, you need to find the first derivative, and its analysis will give you local minimum and maximum, and that should be sufficient to get the graph. Perfect. Now, when you're working with the radical functions, in this case, you should work with both first derivative as well as the second derivative, since concavity matters. Perfect. So that is kind of very important. Second, also look for cusps in this particular case. So whenever we have a radical function, we expect cusp and corners, right? So cusp is definitely there. So you have to look for that while sketching the graph. So nature of the graph is also very important. So I hope all this makes sense. Feel free to write your comment, share your views, and if you like and subscribe to my videos, that'd be great, right? So I hope if there is any difficulty in kind of sketching the graphs, you can always contact me. Here is my email address. So feel free to send me an email, uh, or you can also write a comment on the video itself. I can always help you. Thanks for your time and all the best.